Let's see what are these acid-base indicators. You're already familiar with blue litmus and also red litmus and substance like phenolphthalein, which in short form we write it as HPH, methyl orange, MEOH. Similarly, thymol blue, phenol red, etc. are the substances which when added to aqueous solution of acids or bases exhibit different colors. Let us see, for example, let in this conical flask some amount of HCl solution is put. So to this HCl solution, if you add a drop of methyl orange, what's the color developed? It becomes orange or orange red. Thus, methyl orange has got the property of developing orange red color in acidic medium. Now what happens if we take into the conical flask some amount of acid HCl, and let us now add another substance called phenolphthalein. Phenolphthalein as such is colorless. When it is added 1 drop, 2 drops, 3 drops, still we don't find any change in the color. That is, when phenolphthalein is added to acidic solution like HCl, there is no change in the color. Whereas when substance like methyl orange is added to acidic solution, orange red color is developed. Let us now take certain amount of NaOH solution in a conical flask and let us add 1 drop of methyl orange. Now what is the color developed? We'll find the solution develops yellow color. That is, methyl orange has got the property of giving yellow color to the basic solution. But what happens when phenolphthalein is added now to this NaOH solution? So this is the conical flask in which NaOH solution is once again taken, and let us now add a drop of phenolphthalein. Immediately the solution is turning to pink in color. That is, phenolphthalein develops pink color in basic solution. Thus we find phenolphthalein is one substance which in short form we write it as HPH, which develops no particular color in acidic medium. Solution remains colorless. But the same phenolphthalein when added to an aqueous solution of basic nature, what is the color developed? We could see that the solution develops pink color. Thus phenolphthalein has got the property of giving different colors in aqueous solution. Then what about methyl orange? When a drop of methyl orange is added to an acidic solution, orange or orange red color is developed. Whereas the same drop of methyl orange when added to basic solution, we find the whole solution turning yellow in color. Thereby we conclude that methyl orange has got the property of giving orange red color in acidic medium, whereas in basic solution it develops yellow color. Similarly, we have many substances such as methyl red, blue litmus, red litmus, phenol red, thymol blue, etc. All these substances exhibit different colors in aqueous solution depending upon the acidic or basic nature of the solution. Such substances like phenolphthalein, methyl orange, methyl red, blue litmus or red litmus, phenol red, which develop different colors in aqueous solution depending on the acidic or basic nature of the solution, are called acid-base indicators. And these are also called visual indicators. Let us now discuss Oswald's theory of acid-base indicators. Why do these different substances like phenolphthalein, methyl orange exhibit different colors in aqueous solution? What is the functioning of these indicators to exhibit different colors depending upon acidic or basic nature, which was explained in detail by the scientist Oswald and is known as Oswald theory of acid-base indicators. According to this theory, all indicators are either weak organic acids or weak organic bases. For example, phenolphthalein is a well-known example of weak organic acid, whereas methyl orange is a well-known example of weak organic base. And these indicators being weak organic acids or weak organic bases in aqueous solution undergo ionization to the smaller extent. Say for example, phenolphthalein in aqueous solution undergo ionization to give lesser number of H plus and pH minus ions. Thus, there exists an equilibrium between ionized form of the indicator, that is H plus and pH minus ions, on the left hand side, unionized form of the indicator. Whereas this H plus and pH minus is ionized form of the indicator. and there exists an equilibrium between unionized, that is molecular form of the indicator, and ionized form of the indicator, that is H plus and pH minus. Similarly, methyl orange being a weak organic base, which in short form we write it for the sake of convenience as MEOH, undergo ionization to the very smaller extent in aqueous solution to give Me plus and OH minus ions. This Me plus and OH minus in aqueous solution is nothing but ionized form of the indicator, whereas this MEOH unionized form of the indicator, in other words molecular form. So molecular form or unionized form of the indicator. There exists an equilibrium between this molecular form of the indicator and ionized form of the indicator. If the molecular form of the indicator possesses one particular color, then the ionized form of the indicator possesses another color. For example, the phenolphthalein, the molecular form of the indicator, which is represented in short form as HPH, is colorless, whereas its ionic form pH minus is pink in color. Thus, these different forms of the indicator in aqueous solution possess different colors. And if this molecular form of the indicator, which is colorless as far as phenolphthalein is concerned, exists in acidic medium, then the ionic form of the indicator exists in basic medium. Thus, whenever there is a change in the medium from acidic to basic or basic to acidic, there will be change in the form. Molecular form will be converted into ionic form will be converted into molecular form. With the change in form, there will be change in the color. That's how phenolphthalein exhibits different colors in aqueous solution depending upon acidic or basic nature. In acidic medium, it brings no change in the color. That is, even after the drop of phenolphthalein is added to acidic solution, it still remains colorless. Whereas when a drop of the same phenolphthalein is added to aqueous solution of a base, immediately it turns pink. Similarly, when we take methyl orange, the molecular form of the indicator MEOH is yellow in color. That is, the indicator as such possesses yellow color, whereas its ionic form, which we write in short form as Me plus, possesses orange or orange red color. If the molecular form of the indicator exists in one medium, say this methyl orange in basic medium, then its ionic form will be existing in acidic medium. Thus, whenever the basic medium changes to acidic medium or acidic medium changes into basic medium, then there will be change in the form from molecular form to ionic form or ionic form to molecular form. As a result of which, the solution either will turn to yellow or changes to orange red. So yellow changes to orange red changes to yellow depending upon the nature of the solution, basic or acidic. Thus, phenolphthalein and methyl orange exhibit different colors in aqueous solution depending on the pH of the solution, whether less than 7 or more than 7. That is either acidic medium or basic medium. Let us take an example of phenolphthalein once again. HPH, since this is a weak organic acid, in aqueous solution it undergoes ionization to the smaller extent to give H plus and pH minus. So this HPH form is molecular form or unionized form, and this pH minus of phenolphthalein is nothing but called ionic form. Now what exactly you mean by the molecular form of the indicator changing to ionic form of the indicator with the change in medium? Let us take an example of HCl, that is a strong acidic solution in a beaker. To this, let a drop of indicator phenolphthalein is added. The moment a drop of phenolphthalein indicator is added, there exists an equilibrium between the molecular form of the phenolphthalein and ionic form of the phenolphthalein. And we have discussed that if the molecular form of the indicator exists in acidic medium, the ionic form of the indicator exists in basic medium. Now the moment HPH is added to this aqueous solution of HCl, which contains H plus ions. The moment the drop of phenolphthalein is added to aqueous solution of HCl, as the solution contains large excess of H plus ions, the total H plus in the solution becomes much more. As a result of this common ion effect, the equilibrium shifts towards the left. In other words, the equilibrium is shifting towards the left hand side involving molecular form of the indicator. Therefore, the solution will now contain much more amount of molecular form of the indicator than ionic form of the indicator. And once the solution contains much more amount of the molecular form of the indicator in acidic medium, the solution should have the color of molecular form of the indicator. And what is the molecular form of the indicator phenolphthalein? It is colorless. So thereby, when a drop of this phenolphthalein is added to any aqueous solution of an acid which contains large excess of H plus ions due to common ion effect, equilibrium being shifted towards the left hand side, the solution contains large excess of molecular form than ionic form, and the solution as a whole remains colorless. Now what happens if a drop of the same phenolphthalein is added to the aqueous solution of NaOH? So when you take NaOH solution, this solution will contain large excess of OH minus ions. Now if a drop of phenolphthalein is added to this, as we know that phenolphthalein being in an equilibrium with its ionic form and H plus, we have the system HPH giving H plus plus pH minus. Now since the solution contains large excess of OH minus ions, these OH minus ions in solution immediately combine with the H plus to give water, and as a result of this reaction the H plus ions in the system is decreased and the equilibrium shifts on to the right hand side. The more the shift in the equilibrium to the right hand side, the solution will contain large excess of phenolphthalein ions when compared to that of the molecular form of the indicator, and the ionic form of the phenolphthalein, that is pH minus, possess pink color, and therefore the solution as a whole gets the pink color. Thus, when a drop of phenolphthalein is added to aqueous solution of any strong base, pink color is developed. Whereas when a drop of the same phenolphthalein is added to aqueous solution of any acid, the solution remains colorless. Same is the case with methyl orange. Let us now see what we have discussed is true by adding a drop of phenolphthalein to colorless HCl. So let us take some amount of HCl here. This HCl solution as a whole in general is colorless. Now let a drop of phenolphthalein which is also colorless is added. One drop is added, second drop is added, now third drop. Even after adding 3 drops, we do not find any change in color. Thus we say that phenolphthalein does not develop any particular color when added to an aqueous solution of an acid. But if we add the same phenolphthalein to an aqueous solution of NaOH, let us find what we find as far as the color change is concerned. So here is the conical flask in which let us put some amount of NaOH solution. Now let a drop of phenolphthalein is added. Just when one drop is added into the solution, immediately the solution turned pink in color. So thus we say that phenolphthalein develops pink color in basic solution, whereas develops no color and makes the solution to remain colorless if it is acidic solution. Let us now say about methyl orange. Methyl orange is also a weak organic base. So in aqueous solution, it undergoes ionization to the very smaller extent to give the corresponding ion Me+. So this is the molecular form, and whereas Me+ is ionic form. Now if NaOH solution which is in the form of completely ions, now what happens? Now in NaOH solution there being large excess of OH minus ions, the total OH minus ions in the solution increases, and thereby due to common ion effect the equilibrium shifts onto the left hand side, and thereby the solution contains large excess of the molecular form of methyl orange when compared to that of the ionic form of methyl orange, Me+. Since molecular form of methyl orange possess yellow color, the whole solution now turns yellow. Thus here the equilibrium is shifted towards the left and making the solution to be the one which contains large excess of molecular form. Since molecular form the indicator possess yellow color, the whole solution is turned yellow in color. But now if the HCl solution, so an acidic solution of contains H plus and Cl minus ions. Now to this aqueous solution of HCl, let a drop of methyl orange is added. It undergoes ionization to give Ma plus OH minus. Now since the aqueous solution of acid contains large excess of H plus, these H plus ions immediately combine with the OH minus ions and thereby come out in the form of water, and hence the equilibrium shifts onto the right hand side. The more the shift in the equilibrium to the right hand side, the solution will contain much more amount of Me plus ions in the solution than MeOH form. In other words, the ionic form of the indicator is much more than the molecular form of the indicator. And we know that the ionic form of methyl orange, that is Me plus, possess orange red color, and thereby the whole solution now turns orange red. Thus, methyl orange develops orange red color in acidic medium, whereas in basic medium develops yellow color. Let us see now what happens here by adding a drop of methyl orange to NaOH as well as HCl separately. So here is the conical flask. Now we are adding NaOH solution into the flask. This solution now contains large excess of OH minus ions along with Na plus ions. And now let us add a drop of methyl orange. The solution thus turned completely yellow. What is the reason for it? Here, because of the common ion effect, OH minus, the equilibrium shifted totally onto the left. The solution contains large excess of molecular form and the solution now contains excess of molecular form of the indicator, and therefore the solution is exhibiting the molecular form of the indicator, that is yellow. But whereas when we add the same drop of methyl orange to acidic solution, we can find the difference in the color. So here is the conical flask. Now we are taking small amount of HCl. Let now a drop of methyl orange is added and is turning to orange red. So that's what exactly happens, and find the change in the colors. So this is nothing but called Oswald theory of indicators. Let us now take certain amount of ammonium hydroxide as the weak base. To this weak base, let a drop of phenolphthalein is added. Now, since the solution contains ammonium hydroxide expected to be a base, the moment the drop of phenolphthalein is added, the solution should turn pink. But we don't find the change in the color to pink. Why? That is, why phenolphthalein HPH is not a suitable indicator if the base is weak. Now what is the reason for it? Now, ammonium hydroxide is a weak base, therefore its ionization is less, therefore the aqueous solution contains very less number of OH minus ions. Further, phenolphthalein is a weak acid, undergoes ionization to the very smaller extent to give H plus ions less in number and also phenolphthalein ions. Now this H plus ions combined with the OH minus ions to give water is very less, because the OH minus ions in the solution are less as ammonium hydroxide is a weak base. Therefore the H plus ions taken away by this OH minus in the formation of water is very less. Therefore, even if the equilibrium shifts to the right hand side, it does not shift to the considerable extent, so that even after the shift in the equilibrium, still the solution contains large excess of phenolphthalein molecules. That is, equilibrium is not shifting considerably to the right hand side to have large amount of pH minus. Therefore, the molecular form of the indicator still is large in amount when compared to that of phenolphthalein ions. And hence the solution will exhibit the color of molecular form of the indicator, that is colorless. So even when a drop of phenolphthalein is added to a weak base such as ammonium hydroxide, the solution still remains colorless. What we observed when it was sodium hydroxide, immediately the solution turned pink. But here there is no change. Hence we cannot use phenolphthalein as an indicator. Now if I add methyl orange to an aqueous solution of a weak acid, now I am taking weak acid as acetic acid. This acetic acid, being a weak acid, undergoes ionization to smaller extent, as you know. Therefore, the aqueous solution will contain very less number of H plus ions. Now if I add a drop of methyl orange to it, MuOH. Now MuOH is, being a weak organic base, undergoes ionization to the lesser extent to give less of Me plus and less of OH minus ions. Now this OH minus ions taking away this H plus to result in the formation of water is very less. Thereby the equilibrium shifting onto the right hand side is very less. The system being shifted to the right hand side to the lesser extent, not considerably high, the solution will still contain large excess of molecular form of the indicator, that is MeOH, when compared to that of ionic form of the indicator Me plus. Therefore, the solution will have the color of molecular form of MeOH. What is the color of molecular form of NeOH? Yellow. So the solution remains yellow rather than expected to be orange or orange red. So there is no change in the color. Thus, methyl orange is not a suitable indicator in the case of weak acid. Note, methyl orange, MeOH, is not a suitable indicator if the acid is weak. So this is very important.